All right, good morning or afternoon, everyone. My name is Miss Tarpon, and I teach Earth Science here at Cyber Academy. I probably know some of you, but not all of you. So today we're going to be talking about oceans, which really this is condensed into just one presentation, but there are many, many classes that you can take on just oceans. So we're going to be taking a look today specifically at how does water rotate around the whole world, which it does in many ways, and looking at not only that, but some of the more chemical factors that are involved in that too, like salinity, how much salt is in the water, temperature, is it cold or hot, and other things too, like the moon, believe it or not, affects the water. So think about that. Okay, so just making some connections here, thinking about like, what do we know? Okay, so we know looking at the surface of a lake, just imagine like you're staring out at or the ocean. Like if you've been to the beach, the water's whipping across that lake or that ocean, and you're seeing what? Little ripples in the surface. So that wind is causing what we call wave currents. That's surface, it's on the surface of the ocean or the lake. So only looking at the top few feet there, but yes, that wind is causing those currents. Also, like I mentioned just a minute ago, chemical factors like salinity or physical factors like temperature and density also are going to play a role in what we call deep ocean currents. So we're going to talk more about that, but just keep in mind those chemical and physical factors play a role also into the oceans. And then gravity, of course. Gravity is something that we have every day here on Earth. Also, the moon exhibits gravity too, causing tides. So thinking about these three factors and how they all play a role in the bigger picture of ocean circulation. So this is just in a nutshell what we're going to be looking at today in class. Okay, so waves. What are waves? They come in different, of course, shapes and sizes. But that being said, that's just wind blowing across the surface produces those little surface waves, whether it's ripples or whether it's more of a swell in the ocean. Wind is the driving factor. Of course, the size of those waves depends on how strong is the wind, how long is the wind. So strong and long. And also something called the fetch. Right here is that word. The length of the area the wind blows over. So the larger the area, the larger a wave. All kind of just thinking just common sense wise. So the next slide is a simulation. You're going to pause the video here, watch the simulation, observe how the particles are moving from both a top view, so looking down on the water, and a side view. So pause the video and do this quick little PhET simulation. I'm going to go past it. Fill in your Collaborate board. Okay, welcome back. So what you should have seen there is that waves are actually also a transfer of energy. So the wind is transferring energy to the water particles. So thinking about what is energy? So think about movement. The way the wind is pushing over the water is transferring those liquid particles and whatever else is in there, transferring that energy to move the water. So kinetic energy is what we call that. The energy is then moving through the water particles, like we said. So the wave moves forward, the water particles moving up and down only. So hopefully you caught that in the PhET simulation that you just watched. Another thing that we see with waves is what we call erosion and deposition. If you remember way back from the very first unit where we looked at the rock cycle, remember erosion and deposition was a huge first part of that rock cycle. And so what was one way that erosion could occur? and that was with water. So we do see that on especially shorelines of the coast. So if you think about, just picture in your mind the coast of South Carolina, of Georgia, you may have noticed before that there are these long strands of islands, what we call barrier islands. Those are actually formed from this wave action of what causes that erosion and then deposition to create those barrier islands, basically. So this happens in longshore currents, which basically just means currents going for a long way along the shore to erode and then deposit in other areas. Very important feature in building narrow islands called barrier islands. One great example of barrier islands are the Outer Banks. If you've seen the show, it's actually mostly not filmed in the Outer Banks. Did you know that? Probably, yes. It is filmed around Charleston, Mount Pleasant area, and some of it where I live in Summerville. But not to get too off track with that, the Outer Banks are a good example of barrier islands. They're also along the Georgia coast, like St. Simon's Island, that area. Those are also barrier islands. All right, I'm going to let you guys watch the video. So pause and then restart. Okay, so currents are produced in basically two ways. One is from the wind that we've been talking about, wind blowing the surface of the water, producing currents. And so that's kind of what we're looking at here. But when currents are grouped in, that should say in circular rotation patterns, they're called gyres. And so here you can kind of see, these are the directions of the wind, all these arrows. So we got some coming southwest, some going east, and then some going kind of to the northeast. So this is the wind, and this is actually the ocean surface current pattern. So if you look closely here, if you're familiar with Florida, with fishing maybe off of our East Coast, you've probably heard of the Gulf Stream. And that's one really good example of a gyre or a surface current. So that is warm water being pulled up from the Caribbean around Florida. When I lived in the Keys, it was right here off the Keys, super close, which was nice. But then gets pulled a little bit off the coast, still taking that warm water up to where these are much colder areas. So looking at like Greenland and of course this is Canada over here. I'm not great with geography, but it gets really cold up here, guys. And so we'll talk about what happens up here with deep ocean currents too. But one other thing to consider here is the equator is somewhere down here, like, you know, where the equator is, kind of the middle of the earth. Very warm there. Hopefully you know that. So what else is happening is that some of that heat that's being radiated, and it's super hot in the equator, so the ocean gets really hot. Some of that heat is getting pulled away by these currents. And so the sun plays a big role in the wind too. And the ocean plays a big role in heat distribution around the earth. Okay. All right, so very simply put though, wind is what causes these surface currents. Surface currents form circular patterns called gyres, like the Gulf Stream. Oh, and one other thing I meant to say was the Gulf Stream. So it's really close to Florida down here, but then it's way further off the coast for us South Carolinians. So for example, if my husband wants to go fishing, a lot of the fish like to congregate around these warmer Gulf Stream currents. And so he has to go off the coast like anywhere between 60 to 100 miles when he goes fishing to get to that warmer water, that Gulf Stream. But just something to think about in case any of you guys fish. Okay, so now we're going to take a look at deep currents. So there are also deep ocean currents, not driven by wind at all. We're going to take a look at what those are too. So this is where chemistry kind of plays a little part, or I should say a bigger part, in ocean circulation. Seawater, as you guessed it, is mostly water, so about 96.5% water. The other 3.5% is dissolved salts, mostly. And so you got a nice little pie chart here kind of showing you, in addition to salt, seawater contains dissolved gases like oxygen and carbon dioxide. That's another very important topic. We're not really going to touch on that as much today. We may see a little bit of that later in this unit. But mostly salt, 3.5% salt. Also, you probably heard of it, or you may have heard of it, as 35 parts per thousand. And so that's another way that you can measure just how much of any given solute is in a solvent is parts per thousand, or you may have heard of parts per million. So 3.5%, so that's percent is per 100, or 35 per thousand parts per thousand. A lot of salt. You've probably tasted salt water before. It's pretty salty. And that's 35 parts per thousand. They do vary a little bit around the world. So that's going to be one of the driving factors of these deep ocean currents we're going to look at here in a second. And here we go. So also temperature matters as well. Like I was talking about earlier, you got the equator along the center line of the Earth. Of course, remember it's a sphere, not a flat, two-dimensional Earth. And from there, you can see it's hot, of course, around the equator, being closer to the sun. As you move away in either direction, north and south, it does cool down. So keep temperature in mind too. And we're looking at ocean temperature here, by the way, but air temperature is very similar. Okay, so those two factors together both combine to influence the density of seawater. So temperature, whether it's cold or hot or somewhere in the middle, and salinity, whether it's super salty, even more than 35 parts per thousand in some areas, or maybe a little less salty in some areas. So those two factors, thinking about this. If you've ever had a glass of really cold ice water, you may have even noticed this before. When you drink it, does it feel and look just like tiny bit more thick, viscous, not vicious, than if you had a warm glass of water? That's because it actually is more dense as it gets colder. So the closer to freezing point the water, the denser the water. So, but not when it freezes, because that would be ice, and that's a whole different ballgame. It's actually less dense than water. So just up to that point. Also, so colder water is denser. Salty water is also denser than not salty water, or saltier the water, the more dense the water. So those two things in mind, the areas that are cold and very salty are going to have more dense seawater. So we see these changes with latitude, so where it is on Earth, and with depth. So we've got this nice little diagram here. We're looking at sea surface density, kilograms per meters cubed. And it starts at 1020, the light pink, and then the higher up you go, the more dense. So 1028, this light orange being the highest value. So looking at this map, where do you see that light orange area? So here's the United States, just to give you a frame of reference. Some of those light orange to oranges, reds, oranges, all up in here, pretty dense. Over here, anybody know what this is? That's the Mediterranean. I just gave it away. Down here, of course, we got lots of cold water building out down here on the southern part of the globe around Antarctica. And all around here. So this is Europe, Mediterranean, like we said, getting warmer off the northwest coast of Africa. Pretty actually, relatively speaking, warm. Remember that Gulf Stream is here too. Okay, so coldest, densest areas are going to be areas where water actually sinks because it is cold and dense. We also see density in layers. So surface mixed zone is water being warm and less dense with lower salinity. So it's just going to be the top couple feet of water, basically. Then there's this transition zone. So you probably have felt this before if you've ever swam in the ocean. Well, that's not that great of an example. Maybe if you've swam like kind of deeper down in the ocean or a pool or a lake, decrease in temperature, salinity gets a little bit higher. And so then density is going to increase with that increased salinity and decreased temperature. And then the deep zone is where the water is the coldest, saltiest, and densest in the whole ocean, which is actually 80% of all ocean water is in this deep zone. Okay, so then we have these huge kind of, there's a name for these, I think they're called thermohaline circulation. So temperature and salt influencing circulation, conveyor belts. I've always heard that too. So again, not getting super in depth with this, but thinking about where we saw on the map that we were just looking at a second ago. Remember, this was that really dense area up here, kind of between Canada and Europe, and then of course down Antarctica. Let's go back to this other one. So you see up here, you've got really cold, deep currents pulling that water sinking down once it gets up here. So warmer water sinks and kind of goes along this big oceanic conveyor belt until reaching close to the equator here below India, and then being pulled back up to the surface, gets warm again, and circulates some more. Also, you have it happening over, it kind of goes in one of two directions. So you've got the cold water, deep, cold, getting pulled back up now, and this is on the western coast of the US. So this is like Alaska, California. Now this is deep ocean. So we're not talking about right here next. You're not going to feel this water necessarily. It's relatively warmer, then it gets redistributed around again. So these are deeper ocean currents driven by heat or temperature and salinity. And just a different picture here. This is closer to the surface, the warm water. And then, of course, very deep, cold, salty water is the blue. This really is what drives a lot of what you see happening in the ocean as far as temperature. It pulls heat away from the equator. So it like really helps distribute heat around the whole Earth. All right, I'm gonna let you guys watch that video. So picking back up here. All right, a little bit more on movement of water in the ocean. Surface currents can also cause vertical movement of water called upwelling. So this cold water that's deeper down, we're just looking at that. If it comes to the surface, that's called upwelling. What drives that is usually wind. So a good example of this, here we again are looking at the west coast of the United States. Mexico's down here, and even further down is Central and South America. I think that's what that is, yeah. So wind is the yellow arrows. The wind's kind of going in this rotational convection current, if you will. So the wind's pushing this way off the coast of South America towards the west, and that's pulling up. So think about the wind's moving the water towards the west. So something's going to have to replace that water that's getting pushed away, just because that's how water works. It goes to where there's no water, osmosis. And that's what's happening here. These red arrows are showing us how the water is then being replaced by deeper, cooler water coming up along that surface. So again, like just thinking about water moving, when it moves in one direction, it's going to come up from the deeper parts and be replaced. What comes up with that water is lots of oxygen. Colder water holds more oxygen. Lots of nutrients, because decomposition and that type of thing is happening deeper down in the water. But also there's not as much life to be eating up any of the things that are there. So it's bringing up nutrients and oxygen, basically. So as you can imagine, lots of fish are going to be attracted to that. These areas are known for their great fishing when this upwelling is occurring. Now, it's not always occurring. There are times when winds shift, and you may have heard of El Nino, La Nina. We won't get into that here. But for the most part, these areas are known for great fishing. The opposite of that is downwelling. So where the process of downward movement of ocean water, so it's just basically warmer water being pushed down. So that would happen closer up here towards Pacific Northwest region of the U.S. All right, and I pretty much went over this stuff, but impacts of water movement, moving polar water, like away from the poles, Antarctica, Arctic, not allowing ice to build up more than normal, so mostly, again, the poles, and radiation, the heat budget, distributing heat around the whole globe. So in a nutshell, all these currents help distribute solar radiation heat around the ocean so that water is not getting too cold or too hot. And it takes about 1,000 years to move this water. So thinking of one water molecule, about 1,000 years to move all the way through the whole Earth. All right, I'm gonna let you guys do those on your own. All right, so last little topic here is tides, anatomy of tides. I'm sure you guys have heard of tides before, especially if you're coastal like me. You probably know that we experience 2 high tides and 2 low tides every day. And these are influenced by, of course, the moon. The moon also has gravity, just like the Earth. So here in this diagram, we're looking at what's called the tidal bulge, which follows the moon. So where the water is basically, I mean, and this isn't like true to scale, but think of all this blue as ocean water around the Earth. Where it's thicker, the moon's pulling that water. So it's going to be a bigger tide, basically. And then where it's thinner, it's not happening as much. So the tides are oblong due to the spinning of the Earth plus the moon's gravity. So think of the Earth spinning, rotating, and the moon's gravity. So lots of things kind of work together here. Most shorelines do receive 2 high tides and 2 low tides each day. So just like one example here, so this red dot, think of it as this pier, say it's in Florida. It's experiencing that low tide at 12 o'clock p.m. So the moon's gravitational pull is not affecting this spot at this time of day in Florida. So you can see it's smaller here, that oblong shape is more over here on the sides. So the moon is pulling the water this way. So we're experiencing a low tide at 12 o'clock in Florida. And that's one location. And then later in the day, as the Earth is rotating, like we've said, we've got our high tide occurring at 5 o'clock p.m. So now we're in this location where the tide is much bigger, high tide. And there we go. The moon has gravity. So this is just showing you the gravity of the moon pulling the water and kind of just what that looks like. And then a nice simulation for you to see looking from the top. A little bit crazy if you try to follow those markers around the Earth. Sun is also playing a small role here too. One more. So now we've got this little guy standing on the Earth. So paying attention, here's the moon. Here's the rotation of the Earth. High tide when we're closest to the moon. Low tide when we are on that quarter away from the moon. So 2 high tides, 2 low tides. Now, in tides, we do have a few cases that are what we call extremes. And so this is where The sun plays a role in these extremes too. We have spring tides. We have neap tides. And that's what we're seeing here, spring tides and neap tides. And another thing to pay attention to in this picture is the orange is your solar tide. So sun is playing a small role. The blue is your lunar tide, moon. And then the result of those two together, along with the rotation of Earth, is the resulting tide, so this green color. So see how it's much bigger during the spring tide, much smaller during the neap tide. And that is it. You have a little fill in the blank to do here. Hopefully you guys were able to follow that and get everything filled in the Nearpod, and hopefully all those videos worked for you. So this has been just, again, looking through the oceans, movement of water around the Earth through wind, through gravity, salinity, temperature, all those factors playing a role in how the ocean circulates. And then also that other part, which is tides. And so how coastlines are affected by that gravitational pull of the moon along with the rotation of the Earth. And thank you for joining me today. Have a great day.